If you were asked where the modern world is truly built, you might point to cities, data centers, or financial hubs. You would be wrong. The real foundation of the digital age is forged inside a handful of ultra-secure facilities operated by TSMC. Factories so advanced, so precise, that even the smallest error can ripple across the global economy. These are not ordinary factories. They are the most complex manufacturing systems humanity has ever created. Every smartphone, supercomputer, AI model, and advanced weapon system begins here, not as software, but as matter, as silicon shaped at the scale of atoms. The journey starts long before a single transistor exists. Raw silicon is refined into ultra-pure crystals, grown slowly into cylindrical ingots. These ingots are sliced into wafers so flat that imperfections are measured in fractions of a nanometer. Even a single particle of dust could destroy weeks of work. That is why TSMC's cleanrooms exist. Inside these environments, air is filtered constantly. Temperature and humidity never drift. Workers wear full-body suits, not to protect themselves, but to protect the wafers from them. Humans are the weakest link. Once inside, the process becomes almost entirely automated. Autonomous robots transport wafers inside sealed pods, gliding silently across the floor. Human hands never touch the silicon again. Here, precision replaces speed. The wafers enter the heart of the fab, lithography. This is where the impossible happens. Using extreme ultraviolet light, generated by vaporizing tiny droplets of molten metal, TSMC etches patterns smaller than viruses. Billions of transistors are printed layer by layer, each one aligned with atomic accuracy. If a layer shifts by even a few atoms, the chip fails. There is no room for correction later. This is why artificial intelligence watches everything. Cameras, sensors, and analytics systems monitor every step in real time. AI adjusts parameters mid-process. Light intensity, focus, exposure timing, often faster than humans can perceive. The factory does not wait for mistakes. It prevents them. As wafers move through deposition, etching, and polishing, they are measured constantly. Inline metrology tools scan surfaces, checking thickness, alignment, and structure at nanometer scales. Every wafer generates massive amounts of data. This data feeds predictive models that identify subtle patterns. A tool beginning to drift, a chemical aging slightly faster than expected, a vibration that will cause defects hours later. Problems are solved before they exist. This is the silent power of TSMC. It is not just manufacturing chips, it is manufacturing certainty. After dozens of fabrication cycles, the wafers are complete. They now contain thousands of individual chips, each one a microscopic city of transistors. But fabrication is only the beginning. The wafers are sliced into individual dies, and each die is tested, graded, and sorted. Some perform better than others. Some consume less power. Some handle heat more efficiently. Nothing is wasted. Each chip finds its purpose. Next comes advanced packaging, where TSMC's role becomes even more critical. Modern processors are no longer single pieces of silicon. They are complex assemblies of multiple chiplets, stacked and interconnected in 3 dimensions. Memory is bonded directly to logic. Interposers route signals at extreme speeds. Everything must align perfectly. Robotic arms perform these steps with movements so precise they appear slow. AI vision systems inspect every bond, every connection. If something is off, it is caught instantly. No assumptions are made. At this stage, the chips are alive, but unproven. They enter validation. Electrical tests push them to their limits. Thermal chambers heat and cool them repeatedly. Power efficiency is measured under extreme conditions. The chips are not asked if they work. They are forced to prove it. Throughout this process, the factory learns. Every success and failure feeds into digital twins, virtual replicas of the fab and the chips themselves. These simulations allow TSMC to test changes before making them in the real world. Design and manufacturing merge into one continuous loop. And this loop never stops. As night falls, the factory does not sleep. AI retrains its models using the day's data. Maintenance happens quietly. Schedules adjust. Capacity shifts. By morning, the system is better than it was yesterday. This is why these factories matter so much. They are not just producing components. They are producing the future's physical limits. If this first look inside the world's most advanced chip factories changed how you see technology, hit the like button. Once a chip leaves the clean room, it stops being just a piece of technology. It becomes leverage. Inside TSMC's fabs, every wafer already has a destination long before it is finished. Smartphones, data centers, AI accelerators, autonomous vehicles, defense systems, entire industries depend on what happens here. That dependency is not accidental. Modern chips are so complex that only a few facilities on Earth can manufacture them at scale. And among those, TSMC sits at the center. Its role is not defined by branding or consumer recognition, but by capability. The world does not ask who designs the chip first. It asks who can build it. This reality reshapes global supply chains. Chip designers, some of the most powerful technology companies in existence, rely on TSMC's precision, yield, and reliability. Without these fabs, roadmaps stall. Product launches delay. Entire innovation cycles freeze. And the factory knows this. That is why manufacturing at TSMC is not optimized for speed alone, but for predictability. Customers plan years ahead. Data centers require guarantees. Governments require certainty. So the fab treats uncertainty as a defect. Advanced planning systems forecast demand months and years into the future. Production capacity is allocated dynamically. Tool utilization is balanced continuously. Even power usage is scheduled intelligently to avoid instability. This is manufacturing as coordination. As finished chips move into logistics, traceability becomes critical. Every unit is serialized and linked to its full history, materials, process steps, test data. If a problem appears anywhere in the world, its origin can be traced back instantly. Nothing is anonymous. Distribution itself is a controlled operation. Autonomous systems manage warehouses, shipping routes, and inventory levels. AI optimizes for speed, security, and environmental impact simultaneously. A shipment delayed by hours can cost millions. The system does not allow that. Beyond efficiency lies something more sensitive: geopolitics. These fabs are not just industrial assets. They are strategic assets. Their output influences economic stability, national security, and technological leadership. That is why redundancy is built everywhere. Multiple fabs share knowledge in real time. Process improvements propagate instantly. A breakthrough in one facility strengthens all the others. Even disruptions are modeled in advance: earthquakes, power failures, logistics bottlenecks. The system prepares for scenarios it hopes never occur. At the same time, sustainability becomes unavoidable. These fabs consume vast amounts of energy and water. Without intelligent management, they would be unsustainable at scale. So AI takes control here as well. Water used in fabrication is recycled repeatedly, purified to extreme levels. Energy-intensive steps are scheduled intelligently. Waste heat is captured and reused. Efficiency is not optional. It is survival. Inside the factory, human roles continue to evolve. Engineers do not stand beside machines adjusting dials. They define objectives, constraints, and priorities. AI handles execution, monitoring, and optimization. Humans guide. Machines implement. This partnership allows scale without chaos. As global demand grows, AI training workloads, cloud expansion, edge computing, the factory adapts. New nodes are introduced. Packaging technologies evolve. Yield improves quietly. There are no dramatic announcements when these changes happen. They simply appear, and the world adjusts around them. As night falls, the fabs remain active. Models retrain. Maintenance occurs silently. Digital twins simulate future demand, new designs, and capacity expansions. By morning, the system is sharper. This is how TSMC becomes invisible power. Not through control, but through indispensability. Bell, if you want to continue exploring how these factories quietly shape the world's technology and power structures, subscribe for more deep factory documentaries like this. Every technological era eventually encounters a boundary. For semiconductor manufacturing, that boundary is no longer economic or logistical, it is physical. Inside TSMC's most advanced fabs, engineers are not just building chips. They are negotiating with the laws of nature. As transistors shrink to just a few atoms wide, familiar assumptions break down. Electrons behave unpredictably. Heat becomes harder to remove. Variations once considered negligible become catastrophic. At this scale, manufacturing is no longer about repetition. It is about control. That is why the future of TSMC's factories is inseparable from artificial intelligence. Traditional process control cannot react fast enough, nor see deeply enough, to manage atomic-scale variation. AI fills that gap, monitoring thousands of variables simultaneously, adjusting parameters continuously, and learning from outcomes humans could never correlate. This is not optimization for speed. It is optimization for survival at the edge of physics. One of the most profound shifts happening inside these fabs is the move away from linear progress. In the past, each new node simply meant smaller. Today, progress is multidimensional. New materials replace old ones. Transistor structures change shape. Packaging becomes as important as fabrication itself. TSMC's factories are evolving into systems where design, materials science, and manufacturing converge. Chiplets replace monolithic dies. Vertical stacking increases density without shrinking transistors further. Advanced interposers route signals across microscopic distances with minimal loss. These decisions are not aesthetic. They are necessary, because silicon cannot be pushed forever. That reality forces a different mindset. Instead of asking, how small can we go? The factory asks, how intelligently can we assemble? AI models simulate entire architectures before a single wafer is processed. Digital twins test interactions between materials, heat, power, and time. A change that once took months to validate can now be evaluated virtually in hours. But even with AI, uncertainty remains. And that uncertainty is respected. This is where governance becomes critical. As chips grow more powerful, their applications extend into sensitive domains: defense, infrastructure, surveillance, financial systems. Manufacturing decisions carry consequences beyond performance metrics. So constraints are embedded directly into production logic. Safety margins are enforced automatically. Power ceilings are non-negotiable. Validation includes stability under abnormal conditions, not just peak performance. The factory does not assume best-case scenarios. It prepares for worst-case ones. This approach extends to resilience. Climate events, supply disruptions, geopolitical tensions, none of these are theoretical risks anymore. TSMC's fabs model them continuously. Redundancy is built into systems. Knowledge is distributed. Processes are designed to recover gracefully, not collapse. This is manufacturing with foresight. At the same time, sustainability becomes a defining challenge. Advanced fabs require enormous resources. Without intelligent recycling, reuse, and optimization, they would become untenable. So the factory treats sustainability as a technical problem. Water is purified and reused repeatedly. Energy consumption is forecast and balanced. Waste heat is captured. AI monitors environmental impact in real time, adjusting operations dynamically. The goal is not perfection. It is viability at scale. As the world's reliance on computation deepens, AI everywhere, automation everywhere, the importance of these factories only grows. They are no longer supporting technology. They are enabling civilization's next phase. And yet, their influence remains mostly invisible. Consumers see devices. Engineers see architectures. Governments see supply chains. Few see the factory itself. But here, inside these controlled environments, the future is negotiated between physics and ambition, between intelligence and matter. As night falls, the fab continues its quiet work. Models retrain, tools recalibrate, plans shift subtly. No dramatic changes occur, just improvement, day after day. This is the paradox of advanced manufacturing. The more important it becomes, the less visible it is. TSMC does not need to announce its impact. The world already runs on it. Speech balloon in the comments, tell me, which factory should we go inside next? ASML, Intel, Samsung Foundry, or something even more secretive?